Hi everyone, and welcome to this video titled Statistics, the Language of Psychological Research. In this video, we'll be answering the question, what is statistics? What are descriptive statistics? What are distribution curves? How do we quantify the spread of data? What are inferential statistics? How data can be misinterpreted? And concluding with a review. What is statistics? What are statistics? Statistics is the application of mathematics to describing and analyzing data. What are descriptive statistics? Descriptive statistics merely are the numerical categorization of a data set. And a lot of us already know probably descriptive statistics from high school math courses. Descriptive statistics include measures of central tendency, right? Where the group tends to cluster. Okay? So again, we have three measures of central tendency of clustering groups when we look at how does data spread. We have the mean, or the average of all the scores. So this could be, again, exam scores on a psychology exam. And we could plot and see, take all the students' scores, 30 students in a class, what is the average, right? And then the average would be the mean. And then we could plot that and see if there's a curve or a distribution, which we'll talk about. When reporting the mean, it's preferred for normally distributed data, and I'll show you what that looks like. It's the bell-shaped curve. The median is the middle score in a data set. So we could line all of the scores up in the example of using psychology exam scores, and we could find out what's that middle score after lining up all of the scores. Then there's the mode, which is the most frequent score in the data set. And the median and mode are preferred for skewed data. So let's look at this. So what's a distribution curve? These are distribution curves. They're graphs. They show where scores fall. So if you could imagine that these shaded areas in the top picture, and you could even think about on the two bottom pictures that within those lines, that within them would be various scores, right? So when we talk about a normal distribution, we're talking about what's called the bell-shaped distribution. As you can see, it kind of resembles a bell. And as you can see, the mean or the average scores, most people are clustering where that big hump is. That big hump means that a ton of people are scoring in that range. And we could say, if we wanted, that where you see 0 there, we could say that, let's say we've got a psychology exam of 0 to 100, and most people are scoring 50, for example. And we're not saying good or bad or 50 is bad or anything. We're just saying that might be the average. So what you can see in the distribution curve, the normal distribution, is that most of the scores cluster in the middle, and we see fewer and fewer people, if the frequency of scores at the extreme ends. Okay? If you look at B, that would be a negatively skewed distribution. The elongated tail at the left means that more data in the tail than would be expected in a normal distribution. We have positive skew, where elongated tail at the right, more data in the tail than would be expected in a normal distribution. You can think of this as my statistics research design professor in grad school always said, the tail tells the tale. So it's like, why would you call that a negative skew? Like it looks like most of the scores might be positive, because we look at the tail, right? That what tells us if it's a positive skew or a negative skew. And again, just take some time to chew on this information. It could be a little bit complex, but look at these graphs, read in the textbook, continue to think about this information. But for the most part, a lot of times, a lot of things tend to be normally distributed. How do we quantify the spread of data? Well, we can look at variability. That's the sense of how loose or tightly bunched scores are. So you can see, like, sometimes the distribution might be like really what we call like platykurtic. So it doesn't have the bell shape on it. Okay, that most of the scores are kind of like flat and they're distributed kind of far and wide. But some scores might be leptokurtic, where most of the scores are just in the middle there. Okay, the range is a quantification of the difference between the highest and lowest score. Most of us are probably familiar with range, but that is a way to kind of gauge the distribution of scores. And then we have standard deviation. That's a measure that takes into account how far each data point is from the mean. So when you look back at the graph of the normal distribution, you probably noticed it had 0, and then there was -1 and 1, and then there was -2 and 2, and -3 and 3. Those numbers correspond to distributions or standard deviations. So let's say 0 is our average. The standard deviation of 1 means that 68% of people scored within that range in a normal distribution. Okay? So, like on standard intelligence tests, the average score is 100. A standard deviation is 15 units. So 100 minus 15 minus 100 is 85. 15, the standard deviation unit, plus 100 is 115. So that means 68% of people are expected to fall within that range of scores. But 68% of the human population is expected to score on standardized Q tests between 85 and 115. And then again, you could add another 15 points and be like, okay, a standard deviation of -2 and 2. Well, we would take away 15 points, the standard deviation unit for an intelligence test, from 85, so that'd be 70. And we could add 15 points, the standard deviation for 115, which would be 130. And that'd be 95% of the human population scores between 70 and 130. And you can keep going. But standard deviation is a very, very powerful, very, very useful measure. And it helps us quantify the spread of the data from the mean, how far away people's scores are from the average. Very, very useful. So that's descriptive statistics. We're just merely describing, painting a picture of the data. But psychological scientists and scientists in general, we want to make inferences. We want to generalize our findings in our data set and see, like, does this hold true for most people? Okay, so we want to generalize beyond just describing our data. We want to see, can we generalize this to a larger population? So for example, we have a sample of, let's say, 150 people take an IQ test. We look at their distribution, and we want to see, does this distribution of people taking this IQ test, does that conform? Does that generalize? Can we infer that that matches to most people? Inferential statistics allow us to determine whether we can generalize our findings from our sample to the population. Again, Does our sample, let's say we have 300 participants in our study, do these results generalize to all people with, let's say, depression? Maybe that's our population of interest. Because again, we can't study everybody on the planet or everybody with depression, so we draw samples. We draw samples, and then we look to infer, do our sample data that we have collected, does that generalize to the population of interest? This is done using what's called null hypothesis significance testing. When we talk about statistically significant findings in psychological science, or some people will just say significant difference, or we don't mean great or large. Like significant usually means like, oh my God, this is a big deal. What statistical significance means is that the findings that we found would have occurred by chance less than 5 in 100 times if we use an alpha of less than 0.05, which in general that's the standard cutoff that we use. So when we find, let's say that we find a p-value of less than 0.05. Let's say we have a p-value of 0 or 0.03, which would be less than 0.05. If we did the statistically significant testing and we found that result, we would say that our findings are very unlikely just due to chance. That these results probably occur maybe in different situations and different settings. We may be able to generalize these findings to other situations, people, and those kind of things. So we use the statistical approach when we're making inferences. This is one approach. There are limitations to this approach. This is an intro psych course, so we're not going to go too in depth to this. But for general purposes, when we find statistically significant results, that suggests that our results are unlikely due to chance, that our results probably are a real thing. Then we can look at what are called meta-analyses, and this is the analysis of a set of studies. So we take multiple studies and we analyze the results by lumping all of those studies together on a particular topic that statistically evaluates the strength of patterns across the different studies. It's very helpful. A lot of times we publish single studies, and it can be really useful to say, like, wait a minute, what do all of these results say together? And usually in meta-analyses, we're looking for what's called an effect size, which is related to practical significance. That is, what are the real world importance or real world implications of these results? Like, will these results make a difference in people's lives? Because you can have a statistically significant finding saying something is greater than chance, but it might not have any effect to be meaningful. So for example, let's say that you do a study of a new drug for cancer, and again, you use an experiment, so you randomly assign people to either the new drug group or the placebo group, and you find that no, there were these statistically significant differences for people who received the medication. They had better outcomes than those who received the placebo. Now, you calculated the statistical significance testing, and you found there was a statistically significant difference. You found that the difference between the groups was incredibly unlikely due to chance. Now, the second question we should ask is, okay, like how effective is that new drug? What is the effect size? And that's where, meta-analysis can come in, and I won't belabor that point. But let's say that the results are statistically significant, but let's say that the effect size, the real world impact is negligible. It's like, so do we really want to give people that drug? We've already got these drugs on the market. Like, should we really change course? So a lot of the field looks at, is there an unusual difference? Is there a statistically significant difference, a difference greater than expected by chance? And how impactful is that difference? How much, for example, might this treatment help? Another thing that we can look at when it comes to statistics and data is how data can be misrepresented. If you look at this graph, you can see that on the vertical axis we have arrest rates per month, and then we have time 1 arrest rates and time 2 arrest rates 2 months later. So we're looking at time in months. And you can see here, like, oh my God, that's a pretty big difference between these two groups. And this looks really impressive, right? Like, wow, like that's a really big difference. But let's examine this further. Look at the vertical axis. What does it start with? It starts at 15.5. What does it end with? What is the top? What is the last number? 16. They have truncated, they have shortened, they have cut off parts of the graph. So when you look at the differences between these two groups, you can see the time at time 1, the arrest rates were 15.9, and at time 2, the arrest rates were 15.6. That's only a 0.3 difference, which is really small. But when you look at it the way that it's represented, it looks like a big difference. So this is why we need to be paying attention. How are things being depicted? How are they being visualized? How are they being graphed? And this is an example from arrest rates before and after transcendental meditation. The authors claim, like, hey, we found this difference that transcendental meditation decreases arrest rates. The results, these differences suggest that it probably didn't. I mean, a difference of 0.3 that could have been due to chance, could have been due to anything, could have just been a fluke, right? So make sure you're looking at the graphs and you're investigating them skeptically, and you're looking at how are the data plotted, how are they being represented. So let's review. Statistics is the application of mathematics to describing and analyzing data, like measures of central tendency. So those would be considered descriptive statistics, the numerical categorization of the data set. We also talked about the spread of data, like variability, standard deviations, range. Then we have inferential statistics that allow us to determine whether we can generalize findings from our sample to the population. And finally, beware of how people depict their data with graphs. Thank you for watching. Send me an email if you have questions or comments. Thank you.